Welcome to lab number 11 of GG497 Geological Visualization. Here we're going to move away from drawing cross sections of different features because by now we've seen everything that we can see. We've seen all manner of orientations of beds, from horizontal to vertical to dipping. We've seen folded rocks, we've seen faulted rocks, we've seen unconformities, and next week we'll see a map that has all of those things all happening at once. But this week what we're going to try and do is understand how we can use geological maps to understand geological history specifically. The first half of the lab gives us one of our kind of thought experiment maps, one of our generic maps, which has a series of cross-cutting features that allow you to work out the order of events which have happened to that area. And the second part of the lab asks you to draw a summary geological map from a real geological map of the Cheddar area, and use your summary map to give a relative order of events that have happened to the Cheddar area. So let's consider this geological map for a moment, and feel free to pause this video while you take a look at it. What we can see is a metamorphic sequence of garnet mica schist, marble and quartzite, all of which look, for want of a better word, conformable. The contact between the quartzite and the marble are parallel, or at least similar, to the contact between the marble and the garnet mica schist. So we have this sequence of metamorphosed rocks. Those metamorphosed rocks have been cut by the dike, they have been cut by the fault, they have been deposited, they have had the sandstone deposited on top of them. So these rocks must have existed before anything else, before the sandstone, before the dolerite dike, before the fault happened. So these are probably these are the oldest things that we can see on the map, and we can infer the part of the geological history that's represented by these rocks to be some sort of initial sedimentation that deposited a sequence of mudstones, limestones and sandstones. They're the sort of protoliths to garnet mica schist, marble and quartzite, which have then been metamorphosed and deformed. You can see that those aren't flat-lying rocks. You can see that the contacts between them cut across the topography. So these originally horizontally bedded sedimentary rocks must have been metamorphosed and deformed. That's our first bit of geological history. The next feature in terms of age has to be the dolerite dike. The dolerite dike cuts the metamorphic rocks, but it's been faulted and it's had sandstone deposited on top of it. So those metamorphic rocks must have existed there already in order for the dike to be intruded, and then the dike must have been there already in order for it to be faulted, and the dike must also have been there and eroded down to form an unconformable surface upon which sandstone was deposited. Crucially, we know that this dike must have happened after the metamorphic event, because as you know from earth materials, if you were having a dolerite and you started to metamorphose it, it would turn into some sort of amphibolite. So it's still igneous, it hasn't become a metamorphic rock, so it must have been intruded after the period of metamorphism, but before any other event that we can see on the map. So that's the next in our sequence. So our statement about the geological history at this point would read something like that: a period of magmatism or magmatic activity saw intrusion of a dike set into the metamorphic terrain. We've got these two dikes that are probably radiating out of some magma chamber somewhere else. Okay. The next thing that we can see is we've got to pick between the deposition of our sandstone, the deposition of the sandstone, or the faulting. And what you can see is that the sandstone has been faulted, so the sandstone must have been there already in order for the fault to come along and then displace its contacts. Now, crucially, that sandstone is unconformable. There's an angular unconformity between the sandstone and the metamorphic rocks. You can see that because the sandstone contacts, they're parallel to the ground contours, so the sandstone is bedded horizontally, whereas the metamorphic rocks, they cut across the contours, so they have some element of dip. So there's an angular unconformity between them. So what must have happened is, after the dike was intruded, there was a period of uplift and erosion to produce an unconformable surface, upon which sandstone has been deposited. Then the next thing that must have happened is our fault, because the fault cuts everything, so everything must have already been there in order for the fault to cut through it and displace the contacts. So a period of faulting or tectonic activity produced the northwest-southeast trending faults in the area, northeast-southwest trending faults in the area. Then, obviously, this landscape is still alive, it's still continuing to evolve. We've got the 3 rivers that are cutting down through the bedrock to give us the current topography, so we can finish our geological history by saying that ongoing weathering and erosion process continue to modify the landscape. So to summarize that as a geological history, it really doesn't take that much effort. There isn't a huge amount to write. It doesn't have to be florid prose. Just needs to say what happened in what order and a reasonable description of the environment or the conditions. Okay, so if you can recognize these cross-cutting relationships, you'll be able to finish a geological history no problem. Okay, so that's the first part of our lab. The second part of our lab asks you to produce a summary geological map for the Cheddar Sheet, and on this map you should show significant stratigraphic or lithological boundaries, the main tectonic elements, so major fold axis, faults and so on, and a selection of representative structural measurements and useful labels so we know what's going on in the map. There's a link to this map on Student Central, but if you guys want to copy that link down, then you can just go straight to the map and have it alongside this video. But what I'm going to do is take that map and put it onto our summary grid, which might feel a little bit like cheating, but I can't think of another way to show you how to produce this summary map. Okay, so this is our Cheddar Sheet, and let's just take a moment to have a little look at what's going on in it. I think the most striking feature of this map is this repetition, this symmetry of the beds from our Devonian sandstones and our Carboniferous limestones. And that line of symmetry, it kind of goes along here, which shows this repeated sequence of Devonian to Carboniferous rocks. Now, as we saw in lab number 6 and lab number 7 when we looked at the Newport sheet, this sort of mirror image repetition of the stratigraphy is the sort of outcrop you get when rocks have been folded. So it looks like what we have in this region is a fold with Devonian rocks in the core and Carboniferous rocks on top. So we have some sort of anticline. Then as we go south through our Carboniferous rocks, we can see a similar sort of thing. We can see this stratigraphic repetition, this sort of line of symmetry, and that indicates that we have another fold or another couple of folds. Then what we can see is that there's this angular unconformity between these Carboniferous and Devonian rocks, which are dipping, or they're folded so they have a dip. But if you look at the rocks on top of them that are truncating all of those boundaries, these are our Triassic rocks, which are deposited horizontally and remain horizontal, and they're filling in all of the valleys which cut the stratigraphy. So if you look closely at the topographic contours and the outcrop patterns of these Triassic rocks, you should see that they're more or less parallel, and that means that these Triassic rocks are still horizontally bedded. So we've got this few 100 million years worth of unconformity that marks out the boundary between the very much younger Triassic rocks and the older Devonian and Carboniferous rocks. We can follow that unconformity here, all the way around 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 here. So it's almost like we've got a little window beneath the Triassic to see the Devonian and Carboniferous rocks. Okay, directly on top of that Triassic material, we've got this alluvium, and you can kind of make out all of these farms and all of this stuff that's surrounding this reservoir and the rivers. That's all like made ground or farmland or alluvium, which they've coloured in this light yellow. So I guess technically there's another unconformity between the Triassic and the alluvium. Then in this region we have a collection of some of our Triassic rocks, but those Triassic rocks are in fault contact with some of the Jurassic stratigraphy. So we don't see any of the Jurassic stratigraphy cropping out in the northeast of the area, but we do have some fault bounded blocks of it in the southwest. So those are the main geological elements of our map, and just to summarize those again, we've got folded Devonian and Carboniferous rocks, and I would put a fold axis in there, I'd put another one there, and maybe another little one there. All of those folded rocks are separated from the Triassic by this angular unconformity, so I definitely want to draw that in. On top of those rocks we've got some glacial deposit and alluvium, these browns and yellows. And then in the southwest we've got little fault bounded blocks of Jurassic rocks that are sometimes they're fault bounded against the Triassic material, in other times they have an unconformity between them. So that's what I draw on my summary map. So if we slowly merge the two, hopefully you can see that it doesn't have to be perfect. It just tries to show the main elements of the geological map, so the main contacts, the main fold hinges, the main faults, that sort of thing, and some representative structural measurements that allow us to know what's going on. Okay, so you can replay that a couple of times just to see the how I've managed to construct a summary map, but you can see that it kind of groups all of the Carboniferous rocks into the same package, all of the Devonian into the same package, but it shows the stratigraphic boundary between them because that's a really key one. The main fold axes are shown, the main faults, and the unconformity. So I'm pretty sure all of you guys will be able to recognize those features on maps and should be able to produce a summary for an area. Okay, the next question asks you to describe the geological history of the area shown in the sketch map, giving details about the relative timing of events and the processes involved that have given us our geology. Okay, well, the conformable package of Devonian sandstones and Carboniferous limestones, they're cut by faults, they've been folded, and the boundaries are truncated by this angular unconformity. So everything else has been done to those rocks, so they must have been the oldest ones in the area. So our initial period of geological history suggests that the sedimentation was first deposited a sequence of terrestrial sandstones, as our Devonian all red sandstones, and then later during the Carboniferous, limestones were deposited. So this indicates that there must have been a sea level rise to take you from a terrestrial environment in the Devonian to a marine one in the Carboniferous. Then you can see that the folds and the northwest trending thrust faults, so these guys in here, have affected the Carboniferous and Devonian rocks, but they haven't affected the Jurassic or the Triassic rocks. So those Triassic rocks, for example, are still horizontally bedded, whereas the Devonian and Carboniferous rocks are tilted, tilted and folded. So that period of folding must have happened after the Carboniferous and Devonian were deposited, but before the Triassic rocks were deposited. So what I can say is that tectonic compression formed these northwest-southeast trending folds, and also probably faulted the Carboniferous and Devonian rocks. So these folds that we're seeing here and here, they've been formed from compression. At this point, I don't know which event happened first, the faulting or the folding. I haven't got a cross-cutting relationship or any information about which happened first. So I'm going to put them together as a general tectonic event. Okay, then after all of that tectonic activity happened, there must have been a period of erosion in order to form an angular unconformity between the folded and faulted Carboniferous and Devonian rocks and the horizontally bedded Triassic and Jurassic. Now that unconformity must have happened after the folding, because the rocks on top of it are flat, and it must have happened after that northwest trending faulting, because you can see that that fault abuts and is stopped at the unconformity. It continues beneath it, but hasn't affected any of the rocks above it. So the way I describe that is to say that there must have been a period of uplift, and as we uplifted the ground, we caused it to erode. So we eroded down through our folded Devonian and Carboniferous rocks to form an unconformable surface, upon which Triassic and Jurassic, mostly siliciclastic, mostly sandstones, and some minor carbonates were deposited. Then what you can see in the southwest of the area, there's this north-south trending normal fault, which has faulted the Jurassic and Triassic rocks, but hasn't displaced any of the younger Pleistocene material. It hasn't moved any of this glacial head. You can't follow that fault into the glacial head, so it must have happened pre-Pleistocene, but post deposition of the Jurassic and Triassic rocks. And because it's a normal fault, the way I describe that in geological time is to say that there was a period of extension after the deposition of the Triassic and Jurassic rocks, which caused some of these north-south trending normal faults. then there must be an unconformity. Dozens of tens of millions of years of material has been lost between deposition of Jurassic and Triassic rocks and the Pleistocene deposits, the Ice Age deposits of forming the glacial head. So again, I would describe this as a period of uplift caused the erosion of Jurassic and Triassic rocks to form an unconformable surface, or paraconformable surface, I guess, because everything's still flat, upon which Pleistocene and recent materials have been deposited. And obviously this landscape is still evolving, so I'd say that ongoing weathering and erosion continue to modify this landscape. So again, even though this is a relatively complex geological map, there's quite a lot going on, and there's a few things to take into consideration. You can use very simple cross-cutting relationships to understand the order of events. So all you ever need to write for something like these is a few sentences, 6, 7, 8 bullet points which describe what's going on. Okay, so in your coursework for your map area that you'll be assessed on, we'll be expecting something like this, and this level of detail without being overwritten or too florid. So thanks for watching, guys. I'll see you for the next lab, where you'll be let loose on the Haverfordwest sheet, and then after that I recommend you take a stab at your coursework. Okay, thanks all. See you in the next video.